The Muon experiment that won the 2026 Breakthrough Prize, explained simply. Last month, the Muon G2 collaboration took home the 2026 Breakthrough Prize for a measurement to 11 decimal places. By Physics Explained. On April 18th, at a black tie ceremony in Santa Monica, often called the Oscars of Science, the Breakthrough Prize in Fundamental Physics went to a group of about 200 scientists for measuring one number with extraordinary precision. That number is called the anomalous magnetic moment of the muon. If you're reading this, you're already my kind of audience. I write here on Substack, post companion videos on YouTube, and also share episodes through my podcast. Subscribing is the easiest way to support the work. And if you're able to pledge, it makes a real difference. It sounds like a tiny technical detail, but it became one of the most important precision tests of the Standard Model. For years, this number seemed to disagree with theory, raising the possibility that the muon was quietly pointing toward new physics. That is what made the measurement so important. The experiment was not just asking, what is this number? It was asking whether the Standard Model, our best theory of particle physics, could survive one of the most precise tests ever thrown at it. To understand why this mattered, we need to answer a few questions. What is a muon? What does anomalous magnetic moment mean? How do physicists calculate it? And why did they win this prize? What is a muon? A muon is a heavier, unstable version of the electron. Same electric charge, same spin, about 207 times the mass. It lives for around 2.2 microseconds before decaying. There are three particles like this in nature, called the charged leptons: the electron, the muon, and the tau. They are identical except in mass and lifetime. The electron is light and stable. The tau is heavy and decays almost immediately. The muon sits in between. It was discovered in cosmic rays in 1936, which was a surprise. Nobody had been looking for a second electron, and there was no theoretical reason to expect one. When the physicist Robbie heard about it, he reportedly said, "Who ordered that? We still don't really have an answer. The muon doesn't build atoms or chemistry or any familiar matter. It's just there, a copy of the electron we can't explain. What we can do is use it." What is its anomalous magnetic moment? The property they were studying is the spin of the muons. Every muon has a property called spin. It's something the muon has the way it has electric charge, built in, always present, can't be turned off. Physicists call this kind of property intrinsic. Mass, charge, and spin are all intrinsic. Spin, like many things in quantum mechanics, is quantized. It can only come in specific, discrete amounts. Particles either have an integer spin 0, 1, 2, or a half-integer spin 1/2, 3/2, and nothing in between. The muon, like the electron, is a spin 1/2 particle. The direction of the spin matters too. When you place a muon in a magnetic field, its spin lines up with the field in one of two ways, pointing along it or against it. Physicists call these up and down. There is no third option, no diagonal, no halfway. The magnitude of the spin is fixed, and the orientation is binary. Spin has no classical analog. It is a purely quantum mechanical property, and nothing in everyday experience behaves quite like it. But physicists still find it useful to picture a muon as something like a tiny spinning top, because in some ways it behaves like one. It responds to magnetic fields the way a spinning charge would. The picture is helpful, but not a literal truth. Because the muon has both electric charge and spin, it behaves like a tiny bar magnet. A spinning charge generates a magnetic field, and the muon, carrying charge and spin together, ends up with its own little north and south poles. You can guess what happens next. Put a bar magnet in a magnetic field, and it doesn't just ignore it. If the field is uniform, the magnet feels a torque and tries to turn so it lines up with the field, like a compass needle pointing north. A muon behaves in a similar way, except the tiny magnet is its spin. When a muon is placed in a magnetic field, its spin does not simply snap into place. Instead, it rotates around the field direction like a wobbling top. In physics, this motion is called spin precession. That wobble is the entire game. The rate at which the muon's spin wobbles inside a magnetic field is what the experiment measures. The rate of spin precession follows a simple formula. If the muon has charge Q, mass m, and the magnetic field has strength B, Then the spin precesses at a frequency, g qb/2m. That g is the g factor, the dimensionless number that captures how strongly the muon spin couples to magnetism. Larger g, faster wobble. Stronger b, faster wobble. Everything in the formula is something you can measure. The Fermilab experiment uses a much cleverer trick. The muons are not just sitting in the field. They are circling a giant ring at nearly the speed of light, going around about 150 times every microsecond. That circular motion has its own frequency, called the cyclotron frequency, and it also depends on the magnetic field. Now look at what happens if you subtract the cyclotron frequency from the spin precession frequency. The two formulas share a QB/M factor, and when you do the subtraction, almost everything cancels. The difference between how fast the spin wobbles and how fast the muon goes around the ring depends on G-2/2. That quantity has a name. It is the anomalous magnetic moment of the muon, the very number the experiment is trying to measure. It is also why the experiment is called the Muon G2 experiment. The G factor is the key to everything that comes next, and its history is surprisingly strange. Start with classical physics. Imagine the muon as a tiny ball of charge that is spinning. That picture gives you G=1. In other words, the muon would act like a small magnet, but nothing strange would happen. No surprise. No mystery. Then came Dirac. Then Dirac arrived. In 1928, he wrote down the relativistic quantum wave equation for the electron, and out of it fell something nobody had asked the equation to deliver. The spin of the electron, and the fact that G should equal exactly 2. Not 1. Twice the classical value. The result was so unexpected, and so precisely confirmed by experiment, that it became one of the early triumphs of quantum mechanics. For a point-like spin, 1/2 particle obeying Dirac's equation, G=2 on the nose. It didn't last long. 2 decades later, with the development of quantum field theory, physicists realized that Dirac's equation, beautiful as it was, treated the particle as if it lived alone in empty space. In quantum field theory, no particle lives alone. Around every electron and every muon, virtual particles are constantly flickering into and out of existence. Photons, electron-positron pairs, eventually quarks and W bosons. The real particle is forever wading through this quantum foam, and the foam tugs on it. These quantum fluctuations shift the G factor by a little. And the remarkable thing is, we can calculate that shift. We can sit down and work out, to 10 or 11 decimal places, what an unobservable cloud of virtual particles does to a real one. It is one of the more astonishing things physics can do. How do you calculate it? Quantum field theory gives you a way to calculate what the quantum foam does to the muon. The tool is called a Feynman diagram. A Feynman diagram is a little picture of something the muon can do. Lines for particles, dots where they meet. The simplest picture is just a muon sitting in a magnetic field, and it gives you Dirac's answer, G=2. More interesting pictures show the muon briefly emitting a photon, or a particle pair flickering in and out, or heavier particles making a brief appearance. Each picture is one thing that can happen, and each one tweaks the magnetism a little. The trick is that every picture corresponds to an equation. Feynman wrote down the rules for turning a diagram into math. Convert each line and dot into a specific factor, do the arithmetic, and get a number. So predicting the muon's anomalous magnetic moment works like this. Draw every picture you can think of. Convert each one to math. Add up all the numbers. That sum is your prediction. That's what physicists did, and did understates it. To get a prediction precise enough to compare against the experiment, they had to draw and compute more than 13,000 diagrams. The simpler ones are manageable. The harder ones involving integrals are nightmares and are done with custom-built code by people who specialize in exactly that. Doing 13,000 of them is a multi-decade, multi-continent effort involving hundreds of physicists, careful cross-checks between independent groups, and occasional discoveries that someone somewhere made a sign error 20 years ago. They did it anyway. They drew the diagrams, summed the contributions, and got a number. What did the experiment find, and why did it look, for a while, like the standard model was breaking? Then the experiment measured the same quantity, and the two numbers didn't match. How the experiment actually works is a story for another post. This one is already long. What could be going wrong? Two possibilities. Either the calculation was off somewhere, or the list of particles going into the calculation was incomplete. That second possibility was the exciting one. The prediction includes every particle we know about. If something else was flickering in the quantum foam, something nature has, but we haven't discovered yet, its fingerprint would show up exactly here, as a disagreement between prediction and measurement. For a few years, it really did look like the muon was pointing us toward a particle nobody had ever seen. Let me explain how results are presented in particle physics. To claim a discovery, physicists usually require something called 5 sigma significance. That means the chance that the result is just a random statistical fluctuation is extremely small, about 1 in 3.5 million. In other words, before physicists say, we discovered something, they want to be almost completely sure that the signal is not just noise pretending to be a discovery. At Brookhaven National Laboratory, the muon seemed to disagree with the standard model by about 3.5 sigma. That was not enough to claim a discovery. Particle physicists usually want 5 sigma for that, but it was too interesting to ignore. So the experiment moved to Fermilab, another national lab in the United States, just outside Chicago. And the move itself was almost unbelievable. The giant magnetic storage ring from Brookhaven was too delicate to take apart, so they moved the whole thing. It traveled down the East Coast by barge, around Florida, up the Mississippi River, and then by truck to Fermilab. They literally moved a 50-foot wide ring across the country. Then Fermilab took new data. And after the first result came out, the disagreement with the standard model became even stronger, about 4.2 sigma. Still not enough for a discovery, but definitely enough to make physicists pay attention. Then Fermilab kept going. More data came in. The measurement became sharper and sharper. And in 2025, Fermilab released the final result. The experiment itself was rock solid. The muon really was wobbling at the value they measured. But then the twist came. The disagreement did not grow into a discovery. Instead, the theory changed. The twist came from one specific part of the calculation. Most of the muon, G2 calculation can be done incredibly precisely. But one piece is much harder. It involves the strong force, where quarks and gluons interact in messy ways. This part is called the hadronic vacuum polarization contribution. There are 2 main ways to calculate it. One way is data-driven. You use real experimental data from particle collisions and feed that into the calculation. The other way is lattice QCD. You simulate the strong force directly on a huge spacetime grid using supercomputers. For a long time, the data-driven method was trusted more because it had smaller uncertainties. Lattice QCD was promising, and its central value was closer to the Fermilab measurement, but its error bars were larger. So the famous 4.2 sigma disagreement was quoted using the data-driven standard model prediction. Then things changed. New data-driven results started moving closer to the lattice result. At the same time, lattice QCD calculations improved and their error bars became smaller. Now the standard model prediction sits much closer to the experimental measurement. So the muon G2 anomaly did not disappear because the experiment was wrong. The experiment measured the muon very precisely. What changed was our calculation of what the standard model predicts. The hardest part of the theory moved closer to the experimental value. And because of that, the big disagreement is no longer there. So the story changed. The muon G2 anomaly is no longer a strong hint of new physics. The experiment measured the muon very precisely, and the updated standard model calculation now sits much closer to that measurement. In that sense, the big mystery is mostly finished. But one puzzle remains. The different data-driven calculations do not all agree with each other. Some collision data gives one answer. Other data gives a slightly different answer. And physicists still need to understand why. The lesson here is not that the experiment failed. The lesson is almost the opposite. The experiment became so precise that theory had to catch up. That is a rare and beautiful thing in physics. Usually, we think of theory as leading the way, making predictions for experiments to test. But here, the experiment was pushing harder than the theory calculation could comfortably handle. Even when it did not reveal new physics, it exposed something important. Precision experiments can put pressure not only on nature, but also on our own calculations. And this is why the experimentalists won the Breakthrough Prize. The experimentalists pushed so far that theory had to catch up. Even though the anomaly no longer looks like strong evidence for new physics, the achievement remains huge. They measured the muon with extraordinary precision and forced physicists to understand the Standard Model at a deeper level. That is the real breakthrough. If you want to learn more about the Standard Model in plain language, consider subscribing, and if you can, a pledge helps me dedicate more time to writing and keep the blog going. If you're reading this, you're already my kind of audience. I write here on Substack and post companion videos on YouTube, and also share episodes through my podcast. Subscribing is the easiest way to support the work. And if you're able to pledge, it makes a real difference.